Hello students. So today's class we'll continue with this one last problem. This is the fourth problem which we are doing under static loading, and this problem is of maximum difficulty what you may encounter in the tests and exams. So this is a combined kind of problem. Okay, so you can have either any two of these stresses, and you can experiment with what will happen. So this is a kind of a worst case scenario problem, right? So let's continue with this. So this problem, it was seen that the beam here, the beam or what you can say a rod, is subjected to stresses in all three kinds of stresses what we discussed in initially. Okay, so it is subjected to axial. Okay, and it is subjected to also bending. Also, it is subjected to torque here. So you can see the three forms of torque. The torque is acting, then you have the bending moment is acting in downward, and the axial force, bending force, and the axial force. So all three kinds of force. So in exams or tests, you note that any two might be asked, or even three for this matter. In case of instead of cylindrical, we can give square, like that. So those are the variations which we can have for this. Okay. Right. So let's continue with the problem. So this we solved in the previous class about I think 50% of it, no, 30% of it we solved in the previous class. So what we did was just note down the important data which is required, convert everything into newtons and mm, and bending force, axial force. Also, the first foremost thing we did was finding out these stresses here. Okay, these bending stress, axial stress, and shear stress. So these three stress values we have found. And now going to the second part of this equation is you need to find the principal stresses, that is sigma 1, sigma 2, tau max for both A and B sections. So if you see here, there are two areas. There's section A here and B. A is subjected to compression because of this bending load, and B is subjected to compression, and A is tensile. Sorry, A is tensile and B is subjected to compression because of the applied load. Also, we don't know how it will behave with the applied torque. So to know the behavior exactly, that's why we are finding the principal stresses, right? As per the given question. Okay. So in according to that, we have found the axial stress, which is amounting to this much, and bending stress amounting to this much again, and finally shear stress. We have found the stress components individually. So now our goal is to find each portion what is the value of stress, right? So let's consider each point at a time. So considering, let's consider point A. So that is the critical section, right? So there are two sections. So you have the bar being like this, right? So because of the loading conditions, the torquing and the axial, the bending load, all these things. So there are two portions created. The critical portions are created like this. So this portion here will be like A, and this one is B. So these are the critical points where the failure might occur. So first off, we'll start with A. So when we are starting with point A, let's see the stress values. We can link this using, we have both axial, bending, and shear. So three kinds of stress values. So because of that, we can only link this using the principal stress equations. So that's the only way which you can link all these three kinds of stresses, right? So let's find the stress due to the tensile and bending, the axial and bending. Okay. So I'll say sigma is equal to sigma A, which is axial, plus sigma B, bending. Okay, the sum of both kinds of loads. Let's find out. So sigma A, I think we know, is 7.64. There is 7.64 plus sigma B is a bending stress 61.11. This is 61.11. So this will give us the value of the combined stress. So this I can call it as the combined stress. So this is the combined stress. This is because of axial and bending load. Okay. So this comes to, let me calculate this, 7.64 plus 61.11. Okay, so this is amounting to 68.75 Newton per mm square. So this is the combined stress. Now if I go for shear stress, there is no other combination. So shear stress, I can write it as it is. So this is the value of shear stress. You can write it as it is here. Okay. So now I need to link this. So for linking, I'm using the principal stress. So using principal stress equation, that is sigma 1 comma 2 is equal to. So if you want, we can go back to the data handbook and I can show you what's happening there. Equation 2 point nearby 3, I guess, somewhere near 3 or. So better get a feel of this data handbook, no, before start with the tests and exams and all those. Oh, yeah. Okay. Somewhere over here, I guess. Sigma 1, sigma theta. Yeah, here. So maximum principal stress and minimum principal stress. So these two equations. Okay, and can get extract the data from this. So sigma 1 and 2 just differentiate by one sign here, plus or minus. Let's write this. So that is given by sigma x minus sigma y by 2 plus or minus square root of it's plus here, plus sigma x minus sigma y by 2 whole squared plus tau square, tau xy square. So it is under the root. You can see here it's written as half, right? Half means under the root. So this is equation 2, 34 and 35. Okay. So here you see what all you know. You know two types of stresses. So you know sigma x, that is a combined stress, and this is tau xy. So what we'll do, we'll just equate this for sigma x. So sigma y we'll just eliminate. You don't need to by heart many formulae here. Okay, most of it which are available in the data handbook. So we'll just remove this, make it 0, because we are considering the combined stress case. We'll consider only sigma x and tau, and this equation will get modified. So modify this equation as this is equal to sigma by 2. Instead of x, we just write sigma by 2 plus or minus under the root sigma by 2 the whole square plus tau. Can remove that xy also. Can just write tau square. Okay, so this equation just got modified into this equation. Okay, it's just simplified because of the combined stress condition what we have found out. So now you can just go for substitution. So sigma 1 comma 2 is equal to sigma 1 was 68.75 by 2 plus or minus square root of 68.75 by 2 the whole square plus tau square. Tau was 40.74 square. So with this, we will get our principal stresses. There's principal stresses, minimum and maximum principal stresses both. So sigma 1 and sigma 2 both will you can extract from this particular equation. Just substitute this in the calculator, and I think you might find both the values. So this is nothing but you get maximum stress from this. Sigma 1 most of the time it will be maximum, and this is the minimum principal stress. Okay, so this is in accordance with the question. Also, they have asked one more thing is the shear stress. This is maximum shear stress. Maximum shear stress is equal to tau max. Again, for this, no, you can refer to the data book. So for everything, most of the equations you can refer to. So maximum shear stress here again, you have tau x sigma x minus sigma y whole square. That is only the second part. I told you before, it is just the second part of this equation. If you remember, only half of the second part of the equation from the principal stress. So what you can do is you can just extract this portion here. Okay, I'll write it for you how it looks like. So it will be just like square root of the second part with sigma by 2 whole square, which is the combined stress plus tau square. So this is equation what was that 237. So this will give us the minimum maximum, whereas this here will give us the shear stress, that is tau max. Tau max I told you is just the half portion of this. So what we can do, we can just extract this value here and just paste over here. I think it's simple enough. Right. So let me know the values if you have calculated and calculated. Just let me know in the group chat if you're done. I'll do it in the meantime. So it is 68.75 over 2 squared plus 40.74 squared and root of this. And now it is 68.15 by 2 plus 53.31. Okay, so I'm getting the maximum stress, that is sigma 1. You can just check with me with the answer. I'm getting 87.69 Newton per mm squared positive, whereas the minimum stress is negative. I'm getting minus 18.94 Newton per mm squared. So you can just verify this. So this is our required answer here. Okay, both of these values are the required answers. Then so this portion, let me calculate. So tau max is just, I think you already calculated half part of the previous equation, that came to 53.331 Newton per mm squared. So that was positive. So that is tau max, right? Okay. So yeah, are we done with the problem? No, we are not yet done with the problem. Why? Because you see, we have to consider only point A here. Okay, so same thing, exact same flow of the procedures you need to consider for point B. So again, the doubt arises here. Why did I consider plus here? So I told you, right? Here, point A is being subjected to tensile load because of the bending portion. Bending is positive here. Why? Because it is trying to stretch, or it is tensile here. So only the bending load here is tensile at point A. Okay, again at point A it is tensile. Okay, so that's why for point B I will consider it as compressive because of this load, the bending stress which we are allowing here. What will happen is it will try to press this away, compress this. So therefore, it's not at over. The problem is almost like 75%, but not complete still. So what we'll do, we need to repeat this for point B. So let's consider point B. So now point B, you see here, is subjected to a compressive load. Okay, it is not tensile, it is compressive. So this will become negative. So now my value of combined stress is sigma will be sigma A, that is axial, minus sigma B, that is bending. So axial minus bending force. So that's what I need to do here. So axial stress was, I think, 7. Let me check back. 7.64, 61.11. So this is 7.64 minus 61.11. So this came to negative value of stress, what we can see here. And shear stress is as it is. There is no change in the shear stress tau. So 40.74 as it is. 40.74 Newton per mm square. So 7.64 minus 61.11. You're getting this as a negative. Combined stress as minus 53.47. So negative just means that it's inducing a compressive load, and it is right according to the problem, because point B is subjected to compressive loads, right? So now we have the data. Let's continue with the stress values of the principal stresses. I'm writing principal stresses. Principal stresses, that is maximum and minimum stress. So sigma 1, 2 for this problem, again in the condensed form, is like sigma by 2 plus or minus square root of sigma by 2 the whole square plus tau square. So same like previous step. Only thing changes here, it's negative. That's it. No big change. So it's just a repetitive process. We got 53.47 by 2 plus or minus under the root minus 53.47 by 2 the whole squared plus 40.74 squared. Okay, so you guys can start calculating this and find the value of sigma 1 and sigma 2. You which is giving us directly the maximum and minimum stress values, sigma minimum stress values. So you get that, and one more value is the shear stress, tau max. Tau max is like a maximum shear stress. Okay, again, that is only the half portion of this, so you can just write under the root of sigma x. Oh, sorry, this is sigma. This is the combined stress y2 whole square plus tau square. Again, this is according to the the equation in the data handbook. Okay, so you guys can calculate. Go ahead and calculate and let me know the values. So this will give us the values for shear stress and tensile stress, the combined stress. That is the principal stress, sigma 1 and sigma 2 at section B, as we did in section 1. Let's say 53.47 over 2 squared plus 40.74 squared under the root mi. So minus 53.47 by 2 plus 8.73. Okay, so this time I've got my maximum stress as, let's check with the answer. Check with the answer which I'm writing here. So I got 21.99, almost close to 22 newtons per mm square. Okay, so that's my first answer, and sigma 2 okay, so minus of this, the minimum stress is, I've got minus 75.47 Newton per mm square. Okay, so shear stress is half part of that, so it is 48.73 Newton per mm square. Now see, here there's a confusion. So you are saying here sigma 1 is sigma 1 and sigma 2, but you see the magnitude. You see the magnitude of sigma 2, this is higher in magnitude. Okay, 75.47 compressive is higher, and 21.99 is tensile, is comparatively lesser. So here there's an ambiguity. So this is no longer maximum here. So maximum is this one. So this will just get interchanged. So that's why initially we won't write maximum and minimum. What we write is sigma 1, sigma 2. Later on, whichever value in magnitude comes higher, okay, that will be named as maximum. So at point B, the maximum stress we are encountering is 75.47. That is negative 7.47. And when you come to point A, to go for point A, you are getting maximum as 87.69. So you can directly say that this is more vulnerable. This portion here is more vulnerable. So we need to, for designing or extracting the material properties, no, we need to take this particular value here. This 87.69 tensile at this point A is what the maximum stress is being encountered in this problem, right? So that's how we design. Maximum stress is this. So until we do this, no, find the principal stresses, we won't know which is the critical section. So we don't know whether A is more prone or B is more prone to the failure. So only when you find the principal stresses and check minimum maximum, whichever it is. Only then you come to know which is the weaker point or weaker member here. Also, you can see the shear stress values. So this is point A is 5.3 and point B is around 4.8. So point A is you can say again is more vulnerable here for shear stress. So you take sigma 1 and this tau max for maximum values, and that's how you do solve the problem, right? So that's about this problem. Okay, so any doubts you can let me know in the chat section, right? So okay, so theories of elastic failure is another important topic in your design of machine elements. So these are just empirical theories. You see, whenever a material is subjected to uniaxial stress or axial bending, torsion, so these kind of stresses, it is easy to predict. Okay, just one kind of stress, no, when it is acting, it is easy to predict. But when you have combination of these combined system, whenever you have both axial tension, torsion, pressure, so there are many kinds of loads you can apply on a material, right? So there is pressure, torsion, thermal, so many kinds of stress loading conditions are there. So in those cases, no, it is difficult to predict failure. How will the material behave? How will it fail? So those concepts are difficult, right? So that is why several scientists they have devised the theories of failure. They have formulated these theories of failure so that we can decide whichever is suitable, and we can extract that particular theory of failure. Okay, so for example, we'll start off. There are 6 theories of failure. Okay, so we'll do it one by one, and which is relevant to our course here. So the first one is maximum principal stress theory. So this is also called as Rankine's theory. So Rankine was the scientist who devised this theory of failure. So it is taken for biaxial or triaxial stress states. Okay, biaxial and triaxial stress states. So whenever it reaches its ultimate strength or yield strength of that material, it fails. Okay, so that's what Rankine told, according to the maximum principal stress theory, right? So you can see here on the x-axis this is sigma yield, sigma y is sigma yield, and sigma this is yt is tensile and compressive, and okay, all x-axis and y-axis you have the yield points, and whenever this reaches the principal stress, we already know sigma 1 and sigma 2 are principal stresses. So whenever it reaches that limit, the material will fail. And this region, what you see inside of this diagram, right? So that is called the region of safety. Okay. For principal stress, whenever material falls inside this portion, no, so it is a safe. Okay, so you won't need to draw this. Only then you need to understand how it works. So whenever there is a you have sigma 1 and sigma 2 reaching its values on either side, either compressive or tension. So according to this theory, the material fails or the component fails. That's what he has defined. Next theory is maximum shear stress theory. So previous theory takes into account only the yield stress, that is tensile or compressive, whereas the maximum shear stress theory, also known as Guest's theory. So Guest was the scientist who devised this particular equation. So according to this equation, failure occurs when there is a when the material exceeds this shear stress value of that particular material. Okay, the type of loading whichever you are doing, if it exceeds this stress value, then it fails. That's what this scientist, that is the Guest, has devised. So in this sigma 1, that is the axial loading condition itself, maximum shear stress is taken as sigma 1 by 2. Okay, or yield stress by 2. Okay, when you're considering the maximum shear stress. So this is also seen in the Mohr circle, right? which are studied in MOS perhaps. So these equations also available in the data handbook, so you don't need to by heart them. This theory you need to know. So failure due to maximum shear stress. Any point in the material, if it exceeds that value, it fails. That's what it says. This is a equation in triaxial. Suppose you are having three cases, three shear stress cases. This is 3D case. So whenever you have a, let's say, a 3D body, so for a 3D body, this is how the stress components are depicted. So sigma 1, sigma 2, sigma 3, whenever they're acting, the principal stresses in different planes, this is how it is given. So three-dimensional case, we usually avoid. So only thing is we take the largest value of the yield stress according to this theory. So questions will sometimes be given which theory you have to use, and sometimes you just have to decide. So I'll tell you what are the deciding factors later on. So the third kind of theory of failure is called as the distortion energy theory. So distortion, or is also called as Huber, von Mises, or Henke's theory. Okay, so that's the you might have heard about von Mises. Maybe in finite element methods, most commonly we use von Mises because most of ductile materials, no, they are subjected to, they are easy to find out using von Mises, and this is well proved also. Okay, because it uses distortion energy. So this equations you can see, which is relating directly to strain energy of the particle inside the elemental part. Okay, so according to this theory, you can say the cause of failure is total strain energy. Okay, part of strain energy, it causes uniform extension, and remaining part uniform sharing. So this is known as shear energy. So distortion energy is what predicts the failure, you can say here. So according to this theory, this derivation is not required. So these are all the derivation part. Okay, here one you see over here, no. So this is the form. So it's forming an ellipse. So if you see the equation form of this equation, it's just an ellipse, which gives the value for yield stress or principal stress. This is how you link. So this equation which you see here is what is given in the data handbook. The yield stress over factor of safety is under the root of the principal stresses. Okay, again for maximum shear stress, this is this value we take 0.577 of yield stress. So this you see the region of safety is very precisely known. So this is, if you see quadrant wise, if you analyze quadrant wise, no, this first quadrant, second quadrant, third, and fourth. So if you analyze quadrant wise, it is stronger in tensile. The material is stronger in tensile and stronger in compression. Okay, so that's what it is. You put it in the quadrants of shear, it is not that strong. So this ellipse is why this von Mises stress or distortion energy theory is most widely used in everyday designing life. So this is just the pure shear. If you consider this von Mises stress equation, so if you consider this circle here, okay, if you complete that circle, you will get a state of pure shear, and this is the maximum stress. So this value is nothing but tau shear stress. Shear in yield is equal to this. This is yield stress. The yield stress. So that's how it's related. Almost like 57% of yield stress is regarded as the shear stress values. So if you combine all three theories of failure, no? So these three theories of failure is what we'll be touching on in this course. So rest of the theories of failure, there are like strain energy or Haig's theory, and we have what else? Maybe Saint-Venant's maximum principal strain energy theory, strain theory or normal strain theory. So those two theories we won't cover. So only the first three types. There is the principal stress theory, shear stress theory, and von Mises or distortion energy theory. So these three theories of failure will be primarily concentrating on. So you can see one square here. So this square is what is shown by that um, principal stress theory. So principal stress theory, it states that material is safe in when it falls inside this entire area. Okay, this entire area, it is safe. What it says. But you see this area here, it is not safe according to what? According to our distortion energy or one Mises theory of failure. Okay, so in this case, it is a little bit liberal. Maximum principal stress theory, we can say, is a bit liberal. Okay, so it's a bit liberal, and this tends to add material. Okay, it is not used in optimum cases. So whenever you are designing components like machine beds or the components which are really heavy, then you use the maximum principal stress. So like this, different theories of failure are used in different conditions. So we'll see that in the next slide. Right. So here you see selection. How do you select which theory of failure for which particular problem? So for ductile materials, no, so, we use maximum shear stress and distortion. Distortion, or this is nothing but one Mises theory of failure. Okay, so we use either shear stress theory or distortion theory. Why we don't use the principal stress theory is, I told you before, it is liberal. It is liberal. It will say that it is safe even though it is not safe. So other two theories of failure, they are saying it is not safe, but this theory is saying it is safe. So ductile means we need some, for safety purpose only we are using ductile materials, right? So we should have some warning before the part fails. So that's why we are using the ductile material. But it's showing safe even though not safe, then it defeats the purpose. So that's why we are using the two modified or optimized theories of failure for ductile. Principal stress theory is identical to maximum stress theory in first and third. Okay, this is what I told you. First and third quadrant, there is this similarity, but you can see second and fourth, it is not similar because it is exceeding. This is therefore it is a dangerous to assume that theory of failure. So only you use that when you are very liberal. Go back. So here, see the other two theories of failure. The area falls inside this ellipse here, but only for maximum stress principal stress theory, it shows it is safe. So this region here is a bit dangerous. Okay, so that's why we usually tend to avoid this while we are designing for ductile material. So the compressive strength for brittle material is much higher than tensile strength. Therefore, failure criteria should show a difference. So therefore, it is used for maximum principal stress theory. So in case of compressive stress, right? Okay. So in case of brittle materials, so brittle materials are stronger in compression. So this is the negative area. So this left side of the x-axis here is negative area. So this here it is showing as it is stronger, right? So therefore, in only ductile material, brittle material cases, we use principal stress theory, right? So it depends on material, which material. So if you're using the ductile material, no, so then the maximum shear stress and distortion energy theory are mostly used. And when you're using brittle materials, then principal stress theory is used. So that's how we make the decision based on the type of material. Okay. So whichever material falls in that category, brittle or ductile, we use that particular theory of failure. Again, why? To find the dimensions, obviously, right? So that's it with the theory of what do you say? The theories of failure. So let's start off with the numerical now. First problem: a rod of circular cross section is to sustain a torsional moment of 300 kilonewton meter. Okay, so let's visualize this. You have a component where it is a circular uh, rod or a shaft that is circular in cross section, right? Okay, so it is subject to a torsional moment. So you are applying a torsional moment here. MT is there, and with torsional bending moment of 200 kilonewton. So you also have a bending moment applied on this. So both torsion and bending both are applied. MT and MB both are given. Selecting C45 steel with yield stress 353 megapascal. Assume factor of safety 3. Determine the diameter of rod as per following theories. So this is how the question, typical question will be. Assume any theory, okay, and you tell me what is the diameter of this shaft. So what is the diameter? Assuming these theories of failure. So now you will see really how each theory of failure they affect the value. So maximum normal stress theory is principal stress. So this is nothing but our principal stress theory. Maximum principal stress theory. Then shear stress theory we have not done, right? Distortion is 1 minus. Then total energy. Total energy. In this way. So let's eliminate this. Shear stress theory, distortion energy theory, and the principal stress theory. You have equation for total energy, but for the sake of this subject, let's not do this. Okay, let's remove this total energy theory. So we'll do these three: A, B, and D. That is maximum shear stress, distortion energy, and principal stress theory. Okay, so this is how the loads are subjected to. Let's find out. So MT means shear stress is applied. MB means bending moment is applied. So that is a bending stress is applied. So we only need to link this by using these theories of failure. Okay. Also, you see C45C. C45 is a ductile material. So ideally, you should use these two theories of failure for ductile. Right. So the C45 is a ductile material. So you should use these two ideally. But let's see what the principal stress theory says, or the normal stress theory, what it will show us. Okay. Let's copy this. Let me copy the question along with diagram. Okay, so we are ready. So let's start off. So given or say data given is torque. MT is given as what was the torque? 300 kilonewton meter. So 300 kilonewton meter. So if you convert this to Newton mm, it will be 300 into 10 power. Kilonewton is 3 and meter to mm is again 3. 10 power 3, 10 power 3, 10 power 6. So 10 power 6 Newton mm, and bending moment MB is given as 200 kilonewton meter. So 200 kilonewton meter, which will amount to 200 into 10 power 6 Newton mm. Also given is yield strength of C45 steel. C45 steel is a ductile material. So if they don't give the yield stress, then you have to refer to dead angle. For now, let's simplify our life. Okay, let's give our yield stress as it is in the question. So it is 353 Newton per mm square. So it is given as megapascal. It is Newton per mm square. Then factor of safety is 3. So factor of safety is 3. Okay, determine the diameter of rod. So what we need to find is the diameter of rod. To find is D according to or as per three theories of failure. This first one, maximum shear stress theory. The maximum shear stress theory, and B, distortion energy theory, and last one, principal stress theory. Right. So according to these three theories of failure, we need to find the diameter D. Okay, diameter of this rod here. Okay, so let's start with the solution. So before that, we need the equations, right? So for the equations, we need to go to the dead end. Let's go to dead end. More circle, triaxial, more circle, uniaxial. For torsion, bending. It will be here in the the second chapter itself. You'll find the theories of failure. Just need to check which equation has. Okay, so these are in the fifth chapter. Okay, small, a big jump here. So we have normal stress theory, that is nothing but the principal stress theory, and shear stress theory, and you have von Mises theory. Oh, I think this is again endurance.